Hi, this is Mr. Ward, and here is some more on Chapter 10, Section 1 of Circles Geometry. I'm going to start with number 9 now, because I just did a little bit on 4, 6, and 7, I think it was, at any rate. So here we have, this thing looks like a bicycle, I guess. We're given a circle A is congruent to circle B, and what that tells us, I'll get into what that tells us in a second. And so here's circle A and here's circle B. That means that A and B are the centers. It also tells us their radii are the same. We're also told that AD is parallel to BC. And we're asked to prove that ABCD is a parallelogram. Now, this is actually going to be pretty simple to do as long as you remind yourself of what some of the ways to prove a quadrilateral is a parallelogram. Opposite angles could be congruent. The diagonals could bisect each other. It has two sets of parallel sides. Check all of those possibilities out. There's more. I'm going to ask you to pause the video and see if you can figure out what you have that would allow you to prove this is a parallelogram. All right, assuming you've paused, I will remind you that one way you can prove that a quadrilateral is a parallelogram is if two opposite sides are parallel and congruent. And we have all of that right here. Because we've been told that the two circles are congruent, that means that this and this are the same because they're radii of congruent circles. We also know that side CB or BC is parallel to AD. So those two sides are parallel and congruent, and you'll be able to prove that ABCD is a parallelogram on that basis. Now let's take a look at number 13. Number 13 in here, we have been given circles A and B. When you see the circle with an S in it, that's a symbol for circles, plural. So circles A and B intersect as shown. So we got this diagram with the two circles making a nice little Venn diagram structure. We've also been told that DE is parallel to FC. So we know, I'm just going to go ahead and label this. DE is parallel to FC. We know that ADE, angle ADE, is congruent to angle FCB. And we're also told that DE and FC, remember DE and FC? DE and FC are congruent. So I'm going to make a little congruent mark there as well for both of those. And you need to prove that circle A is congruent to circle B. Hopefully you will pause the video and consider this and see if you can figure it out yourself. And I'm going to hope that you are back from pausing it, and I'll talk about how we can do this. It would be useful to be able to prove that they have the same radii. That's the best way to prove circles are congruent. And since ADE and DE are part of a triangle, and we've got the same type of situation over here, FCB, and they look like they might be congruent, let's see if we can prove that they're congruent. Well, remember that FC and DE are congruent and parallel. And we also know that this angle here, FCB, this angle here, ADE, are congruent. So we could either prove that AD and BC are congruent, but that's actually what we're trying to do anyway, so we're not going to be able to do that until we prove something else. Or we could try to prove that angle AED and BFC are congruent. And we actually can do that because AB is a transversal of two parallel segments. Since it cuts across DE and FC, we can note that this angle here and this angle here, AED and BFC are alternate exterior angles and are therefore congruent because they're alternate exterior angles formed by a transversal cutting two parallel lines. Once we've got that, by angle, side angle, we can prove these little triangles are congruent. AED is congruent to BFC. And by Kappa-Conica, we can say, because corresponding parts of congruent triangles are congruent, BC and AD are congruent, and they are the radii, so these two circles are congruent because they have congruent radii. All right, let's take a look at number 15. We are given circle P, which means P is the center of the circle, and we have parallel sides QT and RS. QT and RS. So let's label that. Go over here. Let's label that. That's parallel, and that's parallel. Now, we need to prove that QR, this segment out here, is congruent to TS. Well, let's start off by thinking about what PQ and PT are. And that's all I'm going to say right now, because I want you to think more about this and try and solve this. So assuming you have paused and you are now back, I'll go ahead and talk about this. So PQ and PT are radii of the same circle, of circle P, so they're congruent. That means that PQT is an isosceles triangle, and that by base angles of an isosceles triangle, those base angles, PTQ and PQT, are congruent. All right, furthermore, angle PQT has to be congruent to angle PRS because they're corresponding angles. PR is a transversal cutting through two parallel lines or segments. And also, PTQ has got to be congruent to PSR by the same reason, corresponding angles. And that tells us that not only are PQ and PT congruent, but PR and PS are congruent because of base angles. This is an isosceles triangle because these two angles, being congruent to those two angles, are congruent to each other. And so by transitive property, these two angles are congruent. So PRS is isosceles, and so PR and PS are congruent. And if that's the case, then by subtraction, we can say that QR and TS are congruent. Okay, let's take a look at number 17. Number 17, we have chords AB and CD are congruent. Okay, we know that. They're congruent in circle P, and circle P means that P is the center. We know that the distance segments, PQ and PR, make right angles. They're perpendicular to those chords. And we need to prove that PQ and PR are congruent. So I would suggest you think about what it means about CD and AB for PQ and PR to be perpendicular to them. What does that tell us about points R and point Q? Think about that. Go ahead and pause the video and see what you can do with this. You might have to draw some lines. So I'm going to assume you have done all of that, and I'm going to go ahead and draw some lines. First of all, I'm going to note that before I draw some lines, I'm going to note that R has to be a midpoint of CD, because a distant segment to a chord perpendicularly bisects it. So those two are congruent. And since Q is also a bisector, because PQ is a perpendicular bisector of AB, those two components are congruent as well. And they're all these CR and DR and BQ and AQ are all congruent to each other because we have cut congruent chords in half. By division, all of those pieces are congruent. All right, now we're going to draw some lines. So I'm going to draw a green line here. Doesn't matter which one I connect. I can connect PA or PB. Those are congruent because they're radii. PD and also PC. Those are all congruent segments because they are radii. And by the no-duh theorem, PQ is itself. Actually, let's hold off. We don't need to deal with that right now. Let me set that aside. That doesn't help us too much. But what does help us is either CR or DR being congruent, and to either AQ or BQ, and also AP and BP and DP and CP. Those are all congruent as well. So that means I can set up a right triangle here. So PRC is a right triangle with a leg and a hypotenuse that are congruent to, say, AQP with a leg and a hypotenuse. So by hypotenuse leg, I can prove that those triangles are congruent. And since those triangles are congruent, PR and PQ are congruent by kappa Kadika. Corresponding parts of congruent triangles are congruent. Okay, now I'm going to look at the last one I assigned so far from chapter 10.1. This is 18. Given circle P, so that is the center of the circle, Z is the midpoint of WX, and WAX, wax, is isosceles with the base of WX. And we want to prove that AZ passes through P. Okay, so let's consider what we know. Remind yourself, first of all, what theorems from way back in chapter 4 about perpendicular bisectors might apply here, because that's going to help you here. And think about what it means that for ZA, that Z is the midpoint and WAX is an isosceles triangle. All right, I'm going to assume you've paused the video so you can consider this, and I'm going to name a few things. The first thing I'm going to name is that we have bisected WX. So WX has been bisected because Z is the midpoint. So we're going to mark this and this as congruent. And the real important thing here is that Z is equidistant to W and X. And we also know that since WAX is isosceles, AW and AX are also congruent. So A is equidistant to the endpoints. That tells us that AZ forms a perpendicular bisector of WX. All right. Now, since this is a circle, I can draw PX and PW as congruent radii. And now I've established that P is equidistant to the endpoints of WX too. And if P is equidistant to the endpoints of WX, it lies on the perpendicular bisector of WX. And AZ makes the perpendicular bisector of AX, because any 2 points that are equidistant for the endpoints of a segment are determine the perpendicular bisector. And so AZ, being the perpendicular bisector, goes through P, which lies on the perpendicular bisector. And that is what I've got. That's a good place to stop. I hope this helped.